Graph Theory Class 2 Video 3. In this video we're going to talk about degree for directed graphs. So let's go to the definition. So unlike the degree for an undirected graph, when you're talking about directed graphs there are two different types of degree. Okay? So if G is a directed graph and V is a vertex, then we have the in degree, which counts how many edges go into V, and we denote it by deg plus V. So there's a plus in the superscript. Okay, so this just counts how many edges are going into the vertex V. And there's the out degree, which counts how many edges are going out of V, and we denote this by deg minus. Okay, so it's a bit more confusing than in the undirected case. In the undirected case, there's no distinction between going in and out. The edges don't have arrows, so in and out doesn't make sense. But when you're talking about the directed graphs, then there is a notion of in and out. So we take this into account. So we have the in degree and the out degree. So let's do an example. Here's some graph, okay? And the question is just to calculate all of the vertex degrees. All of the in and the outs. So let's begin with A. So I need to do two separate things here. I need to calculate the in degree of A, and I need to calculate the out degree of A. So if I draw a circle around A, the in degree is the number of arrows going into A. So that's just that one. Okay? And the out degree is the number of arrows leaving. So that's 1, 2, 3, 4. So this means that the in degree is 1 and the out degree is 4. Let's move on to B. So the in degree of B and the out degree of B. Again, I'll draw a thing. So the in degree is the number of arrows going in. I just see 1. The out degree is the number of arrows going out. And I also see 1. So that's 1, 1. The in degree of C and the out degree of C. So the number of arrows going into C, I see 1, 2. And the number of arrows going out, I just see 1. So this is 2, 1. The in degree of D and the out degree of D. The in degree, I see 2 arrows going in, and I see 1 arrow going out. So that's 2, 1. And finally, let's do E. So for E, I see 2 arrows going in. So the in degree is 2, and I see 1 arrow going out. So it's 2, 1, like that. Okay? This is the complete list of all the in degrees and the out degrees. And if you want an interpretation of this, if you imagine that this graph is a graph of Alice, Bob, Charles, David, and Eve, and the arrows represent who they fancy, or something like this. Okay? So this arrow here means that Alice fancies Eve. Okay? Then the in degree of a vertex is another way of saying how many people fancy that person. And the out degree is another way of saying how many people does that person fancy. Okay? So for example, Alice has a very high out degree, and that translates to the fact that she fancies a lot of people. Yeah? And Charles, David, and Eve have a reasonably high in degree, which translates to multiple people fancy Charles, David, and Eve. Although it's a bit unfair, because for Eve, one of those people is herself. Eve fancies herself. But anyway, this is how you can interpret in degree and out degree. So one more thing I want to talk about is what happens when you add these numbers up. So if I look at the sum of the in degrees, so this is 1 plus 1 plus 2 plus 2 plus 2, which is 8. And if I look at the sum of the out degrees, this is 4 plus 1 plus 1 plus 1 plus 1, which is also 8. And finally, if I look at the number of edges, okay, so that's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and it's not a coincidence that all of these numbers are the same. Okay, and again, if you think about this, I think you can convince yourself why this is true. Like, every edge has a head and a tail. Every edge has one end, which is an arrow going into a vertex, and another end which is coming out of a vertex. So every edge contributes 1 to the in degree sum and the out degree sum. And then when you add up all of those degrees, you get the number of edges. So I can write this formally as a theorem, and I can say if G is a directed graph, then the following are equal. So these three things here are always equal: the sum of all the in degrees, the sum of all the out degrees, and the number of edges. So in a way, it's sort of easier than for the undirected case, because in the undirected case, you had this times 2 multiplier. Okay, in the directed case, there's no times 2 multiplier. So that's degree for directed graphs, and that's the end of this video.